This is a lesson on equilibrium. Some reactions, not very many, but some reactions can go in reverse. Can go in reverse. An example that does not would be like a match. If you burn a match, it's very difficult to get the match to come back. A lot of biological reactions have the capability of switching blood chemistry can go back and forth to keep the blood from being too acidic or too basic. So that's a reversible reaction. If a reversible reaction occurs, then you can make products or you can make reactants. Reactants can go to make products, and the products can go to make reactants. You can make products. This is what we normally have. But you can also have the reverse situation where products can go and form reactants. How does this happen? Let's consider mixing nitrogen gas and 3 moles of hydrogen gas. This is the only stuff you have, so it has to go forward, and so it will make ammonia gas, which has a 2 in front, so it can make 2 NH3. The rate is fast. The rate in the forward direction is fast because there's always concentrations of N2 and H2 at first. Remember from chapter 2 that the rate of reaction depends upon concentration. The more stuff you have, the more likely it is to collide. Therefore, you can make more and more collisions, and the reaction goes fast. After a while, the amount of N2 and H2 decreases a little bit, and the amount of ammonia increases enough so that a little bit of this ammonia sneaks back and makes 3H2 and nitrogen, N2. If you have equilibrium, and I cannot stress this enough, if you have an equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. The symbol, the official real symbol is that. Our textbook uses a double-pointed arrow. Sometimes they use things like up here with 2 arrows. Our textbook uses an arrow like that. But the real official symbol is a double-sided arrow like that. If you show this on a graph, so the rate of the forward rate goes slow. It's fast at first and then it slows down. The reverse speed, goes slow at first. In fact, it's 0 at first, and then it speeds up. If you want to show a graphic of this, you have the rate, and here's the reactants making products. It starts high and it goes down as you decrease the concentrations until it levels off. Here is the products forming reactants. It's 0 at the beginning, and then it goes faster and faster and faster until it levels off. So this is the forward rate, and this is the reverse rate. Very important again, when you have an equilibrium, the rates are equal and opposite. I'll ask equilibrium, the rates are equal and opposite. I'll ask that on many questions. I'll say, what is equal in equilibrium? The answer is the rates, forward and reverse rates. Some reactions get to equilibrium quickly. Some take a long time. There's some chemical I have in an AP lab that I have to set up 3 months in advance to reach equilibrium. It's that slow. Some reactions are fairly quickly, like bloodstream. You don't want to wait a couple of days to see if your blood's going to get the right pH, and then you're dead. So some reactions, some reach equilibrium quickly, others take a long time. In a dynamic equilibrium, the players, the particles, are always switching places. So you're constantly making new ammonia particles, but you're also constantly destroying ammonia and making nitrogen and hydrogen. So even though the relative levels are the same, the numbers or the concentrations are the same, it's the constantly changing. So overall, numbers stay constant, but the individual particles are switching sides. Are changing. The analogy I like using is, say you got Walmart, and the average number of shoppers in Walmart on any afternoon might be 200 people. So over 6 hours, there's going to be 200 people in the store. Are they the same 200 people in the store? No. That would be a static equilibrium where everything stays the same. But you're constantly having people leave the store, and you're also constantly having people enter the store, so that you get an average of 200 people in the store at one time. But in a true dynamic equilibrium, those will stay the same like that. So a dynamic equilibrium, the particles are always changing. In something called a static equilibrium, the individuals stay put. Stay put. It's more like physics where you have a rock on a slope. That's a static equilibrium. It's balanced. If you push a little bit, it'll go rolling down the hill, but it's not moving initially. So it's staying put. You're not constantly getting rocks going down the hill and then coming back up the hill. How can you tell? Tell if there's an equilibrium? Well, you measure the concentrations or the numbers over time. If the concentration or overall numbers don't change over time, then it's an equilibrium. If you have a 2% solution, 98%, 2%, 98% before, and you have 2%, 98% after an hour, 2%, 98% over a day or so, then it's an equilibrium. If you have a 2%, 98% right now, and then in an hour you measure it, it's not 5%, 95%, then that originally is not an equilibrium. If you go to 1585, and it's still not in equilibrium, but if it stays at 1585, 1585 over a series of time, then it is equilibrium. So if the concentration is changing, it's not equilibrium. If the concentration is constant, it is equilibrium. Again, what is equal in equilibrium? Equilibrium. What is equal in equilibrium? big question of the day, the rates.